Thank you, President. Thank you, Cardinal Chancellor, and the organizers for having me here. I'm going to transition from neuroscience to ethical and societal issues in this talk. And the story starts when we discovered that you could use fluorescent measurements of calcium concentration as a proxy for neuronal activity. So this was work that was done together with Larry Katz, with the late Larry Katz, whose memory I honor. And we found that measurements of intracellular free calcium concentration using fluorescent indicators corresponded faithfully to the action potential activity of neurons. So here on the top, you have a patch recording from one neuron, and in the bottom, you can see the fluorescent measurements of calcium. And in this movie, you can appreciate how this is an analyzed movie where we're looking at about 500 neurons in mouse cortical B1. And there's changes in intracellular free calcium that corresponds again to this action potential. The dynamics of these calcium changes are slower than the action potential activity, so it's a low pass version of neuronal activity. But the good news is that within this little patch of cortex, you can see every neuron. So you can simultaneously measure the activity in neuronal populations. So using this method together with the application of two-photon excitation, we and many other groups have started to use calcium imaging in vivo to explore the activity and the function of neuronal circuits. And this is an example of an experiment in which we have a mouse that's running on a wheel, and the mouse is looking at a video screen, and he's awake, behaving, he's running, and simultaneously here on the bottom left, you can see the raw movie of the fluorescent calcium signals from individual neurons. So every one of these dots is a neuron. And the right side here, you can see the analyzed version of this movie. Neurons that are active, which means that they have at least one action potential, they're turning red in this movie. And I hope you can appreciate with your own eye that the activity of the cortex in this mouse, in this corner of mouse visual cortex, is not random, but it has a very distinct dynamics. There are groups of neurons that are firing together. You can see that there are little flashes of activity where neurons fire with other neurons. In fact, you never see individual neurons firing by themselves. The only thing you see is these neuronal ensembles. So the way we analyze these neuronal ensembles is first, we use a computer code to identify the position of every neuron. And for every neuron, we measure the fluorescent intensity as a function of time. Using a spike probability algorithm, we detect the probability that a particular neuron has fired at least an action potential in a particular frame versus time. And using a conservative threshold, we build a raster plot here where every neuron is represented by a line as a function of time. And every one of these black dots represents when the neuron fires at least an action potential. So this is the analysis of the movie that you just saw. And these little ensembles, these groups of neurons that you saw with your own eyes firing together, are seen in this analysis at these little vertical lines of black dots. So they correspond to synchronizations of small groups of neurons. If you collapse this raster plot into a histogram of the percentage of active neurons as a function of time, you see that cortical activity is percolating, and you see these little earthquakes that involve about 5 to 7% of the neurons, which are the ensembles. And you see how there are continuous neuronal ensembles running through the whole movie. So again, with a second conservative threshold, we identify the neurons that belong to each of these ensembles, and we plot them here in these types of maps of an ensemble. So these neurons that are in red fire together at one particular point in the video. So these ensembles occur when we stimulate the visual system of the animal with high contrast moving gratings. These are the same stimuli that you've seen in Peter's talk, the traditional Hubel and Wiesel stimuli. And here are raster plots where the neurons that are participating in ensembles, actually the spikes of the neurons that are participating in ensembles are colored in red. You can see that the activity of the cortex is completely dominated with ensembles. This, by the way, is an underestimate of the number of ensembles. And this happens also if we show the animal a natural movie, a movie of a natural video scenes from, in this case, we take them from BBC documentaries. But if you look at the top, this is the activity of the same neurons in the dark, or when the animal is looking at the gray screen. And you can see that without any visual stimulation, these ensembles are still there. In fact, they dominate cortical activity. So we think that these ensembles could be functional blocks of cortical circuits. And they're there always. They happen in the visual cortex, even if there is no stimulation. And when there is stimulation, when there's visual stimuli, these ensembles get recruited into a visual response. So the suspicion, the hypothesis is that these ensembles is some sort of neural code, that the way that activities is, that the cortex is coding information is through these neuronal ensembles. And to test the hypothesis, we need to manipulate these ensembles. And we do this with an experiment that we call play the piano with the cortex, which means that imagine that each neuron would be a piano key. And we first image the ensemble, just like in the movie that you saw. And here you have one ensemble after the other. And then we play back these ensembles as if we're playing back the piano, the music that we just heard. And we ask the questions if this ensemble have any functional meaning. So in order to play the piano, we need the second laser and a holographic optical device using a spatial light modulator, which is a liquid crystal, which patterns the light in arbitrary spatial temporal patterns. And we do this in 3 dimensions, and we build essentially these light patterns, and we project them back into the cortex. This is an example of Nikolenko, who was a graduate student who had nothing better to do than to write words with and pictures of famous neuroscientists with light and project them back into the brain. So with this piano method, we can stimulate up to about 100 neurons within half a second. Although after we stimulate about 30 neurons, then the patterns get complicated. So effectively, I think in an answer to one question that was posed by Stan earlier in the meeting, you have up to 90 different channels of bandwidth to manipulate cortical activity. So to test if these ensembles are truly functional building blocks, we did an experiment with behavioral task, visual discrimination, in which we train an animal to lick from this spout if the animal sees vertical bars of light that are moving, and we train the animal not to lick if the animal sees horizontal bars of light moving. This is a go, no-go task, and by licking or not licking, the animal tells us what he saw, whether he saw vertical bars or horizontal bars. And simultaneously to this experiment, we're performing 2-photon calcium imaging to map the ensembles that happen in this part of primary visual cortex that correspond retinotopically with the area where we're showing the visual stimuli. So the experiment is we first map the ensembles that are associated with the go stimulus, with the licking of the animal. In this case, these were these vertical bars. Imagine these are the blue cells that participate in an ensemble. And then we map the ensembles that correspond to the no-go stimulus, in this case, the horizontal bar, these green cells. And now comes the interesting experiment. We turn off the visual stimulation and we turn on our piano, and then we activate selectively the neurons that participate in one pattern or the other pattern. This experiment has to be done with two-photon holographic microscopy because these ensembles are intermixed in the cortical territory. And you need to have single-cell resolution because you can have a neuron that belongs to one ensemble sitting next to a neuron that belongs to another ensemble. Because of that, all of this has to be done with holography. And the result of this experiment shown here. So this is, in the bottom is a raster plot. Now we're only plotting the activity of these 9 neurons, which are these blue neurons that belong to this ensemble. And this ensemble is a go ensemble. So this gets activated when the animal receives the go signal. And these blue bars that run through the experiment is when we turn on our piano and we're activating specifically neurons 8 and 9, okay, which are these 2 neurons, which are these neurons in the top. They're part of the ensemble, and they're special neurons. They're neurons that have a property that we call pattern completion, which means that if we turn them on, we can trip the whole ensemble. And this happens during the experiment. At the beginning, we try to turn both neurons on. They turn on, but the rest of the ensemble doesn't care. Sometimes only the top neuron turns on, both turn on, but look what happened here. We turn on both neurons, and the ensemble follows. And when that happens, the animal licks. So if you look at this plot, this is the performance of the animal, the licking, when we recall the ensemble using this optogenetic holographic method, and it's close to full performance, versus when we do not recall the ensemble. So these experiments demonstrate that ensembles are causal, they're functionally necessary, and in other experiments we've proven that they're necessary and sufficient for behavior. So, so this suggests that we've broken one code, or maybe the code, of the cerebral cortex by manipulating these ensembles. At least in primary visual cortex in the mouse, we can make the animal lick or no lick by changing visual perception. In a way, we're introducing hallucinations in the brain of the mouse by turning on the neurons that correspond to the idea of a particular stimulus. These experiments have been repeated and published by other groups, including Carl Dizeros in Stanford, Michael Heuser at UCL, and others. So this code that I'm talking about is actually a combinatorial code. Individual neurons can belong to more than one ensemble. It's a population code. The ensemble is a population of neurons, a small population. It's also distributed. The ensembles that we're mapping, we can only map what we can see. And on a good day, we can monitor the activity of about 2,000 neurons in mouse primary visual cortex. That part of the mouse cortex has 180,000 neurons, and the mouse brain has about 100 million neurons. So we're really looking at a little corner of the brain. I mean, with calcium imaging, we can see every neuron in that little corner, but this is still a little corner of the brain. So our hypothesis is that these ensembles are brain-wide, that we're looking at a little corner of an ensemble that could extend through the brain of the animal. So this work using optical neurotechnology and defining neurotechnology as methods or devices to either record brain activity or to change brain activity proves that you can decode and manipulate brain activity and cortical activity effectively, at least in one part of the cortex in one mammal. And the application of generative AI has also greatly advanced the decoding of brain activity with other neurotechnologies, and we heard a lot already in this meeting about it. I just wanted to show you one example from the work of Eddie Chang at UCSF, who recently recorded the activity of the motor cortex of a woman, a paralyzed woman who had stroke in the brainstem, and so she couldn't talk, no? And feeding these signals using an electroarray, actually in this case was an electrocorticogram, so an intracranial EEG, through a deep learning recurrent neural networks, they built a decoder that synthesized the speech of the woman, what she wanted to say, and also they created an avatar of the woman, and gave the avatar the synthesized speech of the person. And I'm going to show you that demonstration.
I think you are wonderful. You finished. What do you think of my artificial voice?
There's a little bit of echo, but you can appreciate how the woman is talking. She's locked in, yet she's talking with her thoughts, with her internal speech being decoded by this system, and her voice. She's talking to us through her avatar. They've cloned the speech, the internal speech of the woman. Not only they cloned her into an avatar, they've also cloned her emotions and her facial gestures. And this is an example here where you're going to see the avatar making facial expressions that correspond to particular states of emotion. So they're unlocking the woman and giving her the ability to talk and to express emotions and communicate effectively through this avatar by using the generative AI. So, so this is fantastic. As an ex-medic and a researcher, I couldn't be happier. Now we have neurotechnologies advancing quickly. We can decode and manipulate brain activity, and this, of course, is fantastic to understand, to break the neural code of the cortex of the brain, to try to help patients like this woman. But with great power comes great responsibility. As you know, the brain is not just another organ in the body, it happens to be the organ that generates the mind. So all of our cognitive and mental abilities are generated by the brain. And here we have in our hands, in history, for the first time, a technology that enables us to go into this black box. And by recording and manipulating brain activity, by definition, we will be able to record and manipulate mental activity. So because of this, a group of 25 of us, representing the Brain Initiative from the US, Europe, China, including actually a colleague that Mumin Pu sent to this meeting from Japan, South Korea, Canada, Israel, Australia. We also with representatives from the industry in Silicon Valley, from neurotechnology companies, from bioethics, from the law. We got together at Columbia in the Morningside campus, and we call ourselves the Morningside Group in 2017 to study the ethical and societal issues of neurotechnology. And we met in this building, which is right next to the building, which is a national monument in the US, where they started the Manhattan Project. In the basement of this building, which is the Physical Sciences Lab, they built the first atomic reactor in the world. And 2 generations ago, the physicists built the first atomic bomb. They took it from here to Los Alamos to prevent German spies. So you should know that the physicists that built the atomic bomb were the first ones to ask for a regulation at the international level of atomic energy. And through their advocacy, the UN created the Atomic Energy Agency in Vienna in the 1950s, who's overseeing the use of atomic energy, peaceful and military uses, fingers crossed, without any mistake since then. So after 3 days of deliberation, the team, I speak on behalf of them, the Morningside Group, concluded that this is a human rights issue. In fact, if this is not a human rights issue, what is a human rights issue? If you have a technology that lets us get to record and change mental activity, the mental activity is what defines a human being. So this is the essence of who we are now. And we came up with the term neurorights to define new types of human rights that would protect brain activity from inappropriate uses of neurotechnology. We came up with 5 neurorights: the right to our mental privacy, so that the data from our brain cannot be decoded without our consent; the right to our own identity. Already from DBS patients in Parkinson, there's cases where the personality of the patient has been changed with neurotechnology. The right to our own agency. This is what also other people have called a cognitive liberty or free will, so that the decisions taken by our own brain are not cajoled or influenced with the use of neurotechnology from the outside. We also suggested that it's necessary to guarantee a fair access to mental and cognitive augmentation. This is something that we think is in the future. It's unavoidable. It will happen. It's just a matter of time. Humans have always augmented ourselves, and we plan cognitive abilities. When that moment comes, we think this should be ushered under the universal principle of justice to prevent humanity, where some of the population is augmented and some of them is not. And finally, we think that neurotechnology should be particularly careful to protect the users from the introduction of potential biases and discriminations in the algorithms that are used in neurotechnology, because this information is piping right inside the brain and is interpreted as part of yourself. So these pictures are the Museum of the Memory in Santiago, Chile. In the walls of this museum, it's a museum to human rights, and you have written the Universal Declaration of Human Rights. And we would argue that this Universal Declaration covers essentially the human body, and now we have to protect human brain. And this is the the UN Palace in Geneva. So we think that human rights are essentially the purview of the United Nations, and we have been interactive since we published this paper, the Morningside paper in Nature in 2017 as a platform paper. We've been working with the UN to examine the current human rights treaties, and this is a commission from the Secretary General of the UN who asked us to do that. Secretary General Guterres, in his common agenda, proposed that one of the priorities of the UN is to update the human rights regulation, including the Universal Declaration that has not been touched in the last 75 years, and the world has changed a lot. So what we did is what we call a gap analysis. This is a technical term from the legal field, and this involves comparing the protection which is currently present in the major human rights treaties in the world, which are listed here. Okay, besides the Universal Declaration, maybe the most important one is this second one, International Covenant of Civil and Political Rights. This is the human rights treaty that protects your right to free thought. And we compare these protections that exist today with these challenges that we call neurorights. And our conclusion, which was submitted to the UN last year, is that the existing framework of international human rights treaties are not sufficient to protect these areas of concern that I described earlier, that we need to update the international system of human rights to provide additional protection for brain activity, to protect mental privacy, to protect our own mental identity, our own agency, and potentially also to guarantee the lack of discrimination in terms of mental augmentation and lack of bias. So the other thing that I wanted to share with you is that we've also studied, there's 2 types of neurotechnology. There's medical neurotechnology that's used in the hospitals, and there's consumer neurotechnology that's used outside the hospitals. The medical neurotechnology is not of concern to us because it's already regulated, because medical devices are regulated worldwide, And sensitive medical data is already regulated in most part of the world through decades of well-crafted or at least chiseled regulation. But we're worried about the consumer neurotechnology and to study what is the status of consumer neurotechnology. We studied the consumer user agreements of 30 neurotechnology companies, which do not include NextMind, by the way. We didn't study that consumer user agreement. And those is the little print that you have to click, I agree, before you turn on the device or before you download the software. This is the little print that's pages and pages that you scroll through that nobody reads. Well, we read it carefully. And this is an example of one of these consumer user agreements. And the conclusion that we drew is that from the 30 companies that we study, in every single case, the user gives the company complete rights to his or her neural data. And that means that the company can do whatever they want with it. They can decode it, they can destroy it, and in most of these consumer user agreements, the user gives the company the right to sell it to a third party, which by definition legally is not bound to the consumer user agreement. The bottom line, neural data could not be less protected. Our conclusion in one word is consumer user agreements are predatory. And the reason they're predatory is because there's no regulation anywhere in the world that regulates consumer neurotechnology. So there is one exception, and this is the Republic of Chile. So 2 years ago, just about now, the Senate of Chile introduced a constitutional amendment to protect brain activity, here we go, and the information coming from it. A very brief sentence, but this is the first time in history that there's protection for brain data and brain activity. This amendment to Article 19 of the Chilean Constitution was approved unanimously with all political parties behind in the Senate of Chile, in the House, and signed into the law by President Piñera. So this protection at the human rights level in the Constitution in Chile has led to the first case in the neurotechnology court case, Girardi versus Emotiv. Girardi is a citizen Chile here. Emotiv is an American neurotechnology company, and he sued the company for infringement of his constitutional rights because Emotiv is one of these companies that whose consumer user agreements is predatory and takes all the data of the user. So the Supreme Court in Chile just recently ruled unanimously that the citizen was right and forced Emotiv to delete all the brain data from the citizen and to subject itself to inspection by the medical authorities. So this is the first case of jurisprudence based on a constitutional amendment in one country that could open the way to future court cases where brain data is protected, at least in this country. So just to finish, my message to you is, first of all, I'm very bullish about neurotechnology. I've worked my whole life developing new technology to try to understand how the cortex works. I think neurotechnology is great for science, for medicine, and it could be very good for society and also for the economy. Why not? It could lead to a new field of the economy with great benefits for everyone. Also, I should mention that these are early days, so there's probably about 50 companies selling consumer neurotechnology products all over the world. There's still a relatively primitive industry, but it's growing very strongly. I think our estimate is that this year it will be worth $30 billion and growing about 30% per year. And these companies are starting to collect data. As I'm showing to you, this data is getting now essentially stored as a commodity that can be decoded later, or it could be sold to another party, or it could be sold to data brokers. My argument is that brain data is not just any good old data, it's a particular sensitive type of data. In fact, I would argue it's the most sensitive data because it reflects the workings of the brain, which essentially generates the human mind, which generates who we are. So I cannot think of any more data that's more sensitive than brain data, and because of that, it should be specially protected. There's no regulation except for Chile, and from our point of view, there are many different ways of tackling this problem, as I show here. You could propose ethical guidelines, and there's already more than 20 ethical guidelines for neural data. You could also use technical solutions, including cryptography, differential privacy, federated learning. These are all excellent ideas, and they're starting to be looked at, although they're not implemented yet, as far as I know. There's also a medical model, which is to apply to consumer neurotechnology the exact same rules that applies to medical neurotechnology, both for devices, subject them to the inspection of FDA, for example, in the US, or for the data, treating all neural data as health-sensitive data and applying to it the same rigor that's applied in terms of anonymization and lack of commerce of sensitive medical data. But our point of view is that this is maybe a time to reflect about the broader direction of neurotechnology, and maybe the best protection could be or should be at the human rights level, because the human rights level is sort of the trunk of that it's anchored in the concept of human dignity and permeates all of the constitutions and all of the political systems in the world. So with that, I wanted to finish. The work that I presented to you on Neurorights has been done by the very devoted team of people. Most of them work pro bono without getting paid, and led by me and Jared Genser, who's an international human rights lawyer, whose day job is to rescue political prisoners from the prisons of totalitarian regimes. No? And we've done advocacy work, not just in the UN and in Chile, but in other countries in Latin America, in the US, and more recently in Europe, in Brussels, as well as in Australia. And just wanted to finish with a quote from my mentor in Cambridge, Sidney Brenner, who said that progress in science depends on new techniques, new discoveries, and new ideas, probably in that order. And I'm delighted to speak here in a meeting focused on techniques, on neurotechnology. And as you've seen from this meeting, this has broad implications for science, for medicine, and also for society. Thank you.